So we've got the complete Bernoulli equation here. If you want to compare 2 points in a fluid system, how would you be able to tell whether or not these things are actually relevant? Like, for instance, are there any circumstances where you could just ignore one of these terms entirely?
If it's not moving, you would ignore velocity. And I guess you would also ignore IR, because if I is equal to A times velocity, then there would be no flow rate.
Yeah. So in any system where the fluid is stationary, if there's no motion at all, then you can ignore both of the terms that involve motion. And this is usually what we call a hydrostatic system. In a hydrostatic system, there's no motion at all. The fluid is not moving. And so you end up with delta P plus rho G delta Y. No speed term, because if the fluid's not moving, speed here is 0, speed there is 0, there's no change. There's no IR because there's no current. Current represents flow of fluid. If the fluid's not flowing, then I is 0. There might be a pump. But let's say there's no pump at all. Let's say we just have water staying still with no pump. Then we get this vastly simplified version of the Bernoulli equation. The hydrostatic Bernoulli equation says that in a fluid system with no motion at all and no pump, change in pressure plus rho times G times change in height has to add up to 0. Which means change in pressure is directly proportional to change in height. And this is very convenient because it makes it extremely predictable. You move down in water some distance and you gain a certain amount of pressure. You move up in water some distance, you lose a certain amount of pressure. And to convert back and forth between height changes and pressure changes, all you need to do is multiply by density and gravity. In fact, in water, this becomes even more predictable just because we already know the density. What is the density of water?
1 gram per centimeter cubed.
Yeah, 1 gram per cubic centimeter. Or if we want to put that in often more convenient units, 1,000 kilograms per cubic meter. Since a kilogram is 1,000 grams, but a cubic meter is 1,000,000 cubic centimeters, so you end up with a difference of 1,000. So density of water, 1,000 kilograms per cubic meter, very convenient number just because the metric system is defined in terms of properties of water. So 1,000 for density. And what's gravity on Earth?
9.81 or 10.
Yeah. If we just round that off to about 10, rho times G, 1,000 times 10 would be 10,000. So that means if you move down in water a certain distance in meters, you can just multiply that distance by 10,000 to get the difference in pressure. Move down 1 meter in water, gain 10,000. And if you work out the units here, 1 meter times meters per second squared times kilograms per cubic meter, you end up with pascals. And of course, the thousands is kind of unwieldy there, so 10,000, we often just write as 10 kilopascals. So this is a convenient rule of thumb to remember. If every meter you move down in water, you gain about 10 kilopascals of pressure. And that's a nice big round number, again, because the metric system is defined in terms of properties of water. And do you remember how much 1 atmosphere of pressure is?
101 point something kilopascals.
The atmospheric pressure, 1 atmosphere of pressure, is, I think it's 101.3 kilopascals. But if we round that off to about 100, how many meters down do you have to go to gain an extra 100 kilopascals of pressure?
10 times more?
Yeah, you'd have to get 10 times that much. In other words, you'd have to go down 10 meters. So every 1 meter you move down is 10 kilopascals of extra pressure, approximately. Every 10 meters you move down is about 100 kilopascals, which is pretty close to 1 atmosphere. So 10 meters down in water is approximately equal to 1 atmosphere, or plus 1 atmosphere of extra pressure. And note that that's plus 1 more atmosphere above and beyond what you started with. If you're on the surface of the ocean, how much pressure do you already have, even if you're not under the water at all?
1 atm?
Yeah, you're under the atmosphere itself. All that air pushing down on you is 1 atmosphere of pressure. If you then, from the surface, go down 10 meters, you get plus 1 more atmosphere of pressure from the water. So you've got 1 atmosphere of pressure from the air plus one more atm of pressure from the water. You're now at a pressure of 2 atmospheres, 2 atm. Another 10 meters down, you get another plus 1 atmosphere. Every 10 meters down you go in water, you get an extra plus 100 kilopascals of pressure, plus 1 atmosphere of pressure. Any questions on that so far? And that general idea should be true in any hydrostatic system. Anytime you've got fluid that's not moving and there's no pump, it's going to behave exactly like this. Of course, if it's not water, you're going to be using a different value for density. And if it's not on Earth, you'd be using a different value for gravity. But the mathematical principle still applies even if the numbers are different. Also, one other note on the subject, while we're on the subject of diving, going under some water. Let's say here's the water level. And you're right here at the surface, and then you dive down to, let's say you dive down 50 meters. At the top, what's your pressure? How much pressure would you be experiencing at the top there? Yeah, 1 atmosphere, which would be, let's round that off to 100 kilopascals. Dive down 50 meters, how much more pressure do you get? If you're losing 50 meters of height, then you're going to be gaining how much pressure? Yeah, 500 kilopascals. Because delta Y is 50 meters. We already found that rho is 1,000, G is 10, so 10,000. 10,000 times 50 is 500,000, so 500 kilopascals. So you gain 500 kilopascals of pressure. And your final pressure at the bottom would be 600 kilopascals, also known as 6 atmospheres. However, there's 2 different ways you can describe this pressure. What we're looking at here is what's called absolute pressure. Absolute pressure is what the pressure actually is. At this point, the actual pressure, the absolute pressure is 100,000 pascals because of all the air pressing down on you. Down in the deeps here, the pressure is actually 600 kilopascals. because you've got all the air plus all this water pushing down on you. But we can also describe this pressure in terms of what's called gauge pressure. Absolute pressure is what the pressure actually is, but gauge pressure is basically a measured difference. And the reason we call this gauge pressure is a pressure gauge, a tool for measuring pressure. Like, have you seen the tools used for measuring air pressure in a bicycle tire? Like just this cylinder that you plug into the tire and a stick pops out of it? The reason that stick pops out is because of a difference in pressure. You've got the high pressure inside the tire and lower pressure outside the tire. That difference in pressure makes the stick pop out. And the more different the pressures are, the more the stick pops out, and therefore you see a higher difference in pressure. But gauge pressure doesn't represent what the pressure actually is. Gauge pressure is how different the pressure is from the atmosphere. So gauge pressure is the difference between absolute pressure and atmospheric pressure. So at this point, for instance, how different is the actual pressure from atmospheric pressure? The actual absolute pressure is 600 kilopascals, but how much above and beyond 1 atmosphere is that? Yeah, it's 1 atmosphere plus an extra 5 atmospheres. So at this location, we'd say the gauge pressure is 500 kilopascals, or 5 atmospheres. That doesn't mean your pressure is actually 5 atmospheres. It means your pressure is 5 atmospheres more than atmospheric pressure. So these are just two different ways of describing the same situation. At this location, the absolute pressure, the actual pressure felt, is 600 kilopascals. But the gauge pressure that would be measured, that is how much above and beyond the reference point, is 500 kilopascals. I see this as being a lot like the difference between Celsius and Kelvin. Kelvin tells you what the temperature actually is. Celsius tells you how far the temperature is from a reference point, specifically the freezing point of water. Same idea here. Absolute pressure tells you what the pressure actually is. Gauge pressure tells you how far the pressure is from some reference point, specifically the atmospheric pressure. Also, if you're at the surface, what would the gauge pressure be?
Zero?
Yeah, if we go by this strict definition, the gauge pressure is the actual absolute pressure minus 1 atmosphere. Absolute pressure minus 1 atmosphere, in this case, would be 0. So the atmosphere itself is treated as having 0 pressure if we're looking at the gauge pressure, because it's the reference point. If gauge pressure is how far are you from the reference point, and you're at the reference point, you're 0 away from the reference point. Another important thing to consider, what's going to happen if you're at a pressure that's less than 1 atmosphere? Like, let's say you've got a sealed chamber and you pump some of the air out of it, so you make it lower pressure than the atmosphere. If the pressure becomes lower than atmospheric pressure, what would the new gauge pressure be? That is, if you're already at 0 as the gauge pressure, and you make the pressure even lower, what sort of number would that become? Yeah, it's going to be negative. It is possible to have a negative value for gauge pressure. Gauge pressure being a negative number just means your pressure is lower than the reference point, lower than 101 kilopascals. It's impossible for absolute pressure to be negative, though. 0 absolute pressure genuinely means no pressure at all. You can't go lower than no pressure. But 0 gauge pressure just means you're at the reference point. And you can go below the reference point. You can have less pressure than the atmosphere. So gauge pressure can be negative. That just means lower pressure than the atmosphere around you. But absolute pressure cannot be negative. Gauge pressure could go as low as negative 100 kilopascals. So absolute 0 pressure would be a gauge pressure of negative 1 atmosphere, negative 100 kilopascals. Any questions on that? So keep the difference in mind between those as we go forward. Sometimes we'll be using gauge pressure, sometimes we'll be using absolute pressure, and you convert back and forth between them by either adding or subtracting 1 atmosphere. Just like you convert between Celsius and Kelvin by adding or subtracting 273. And also, just like with temperature, if you're talking about a difference in pressure, it doesn't matter if you're using gauge pressure or absolute pressure, as long as you're consistent about it. Because if you use gauge pressure, everything has an extra +1 atmosphere, but when you subtract final minus initial, the extra +1 atmospheres cancel out anyway. Any questions on that so far? So let's take another look at the other terms in the Bernoulli equation, now that we've taken a look at the hydrostatic system. One other quick thing about a hydrostatic system, what's going to happen if 2 points are at the exact same altitude, exact same height?
Then the rho g delta y term will be 0. So that means that the change in pressure is 0.
Yeah, no difference in height means no difference in pressure. But that's only true for hydrostatic systems. If it's not hydrostatic, if the fluid is moving, there can be other terms that throw that off. So you can only assume same pressure means same height if it's hydrostatic. So taking a look at some of the other terms. Actually going back to this delta V squared term, we know there's no difference in speed if the fluid's not moving. Is there any situation where the fluid is moving, but you know that 2 points have to have the same speed? When can you conclude that 2 locations in a pipe have to be moving at the same speed?
If the area isn't changing, then the speed would be the same.
If you've got 2 points in a pipe, even if there's some changes in between, as long as the area at the beginning and the area at the end, let's say we call this point 1 and point 2, as long as these 2 locations have the same cross-sectional area, then the fluid inside has to be moving at the same speed. So same area means same speed because of the continuity principle. A1 V1 equals A2 V2. So that means no change in speed, which means this term can be ignored. So you can ignore this term completely if the 2 points have the same cross-sectional area, or regardless of the shape, if the fluid is not moving, this term is going to be 0. What about the rho g delta y term? Are there any circumstances where we can ignore that?
If there's no change in height?
Yeah, if there's no change in height. And note that that's specifically just comparing this point and this point, point 1 and point 2. What's happening in between doesn't really matter. And by height here, we mean absolute altitude of those 2 locations. We're not really talking about like how deep under a surface it is. You just look at the 2 points you're comparing and compare their absolute altitudes. So if you have, for instance, a hose with a bump in it like this, and you're comparing point 1 and point 2, 1 and 2 are at the same height. Even though there's some changes in height in between, delta only cares about initial and final values. So if this location and this location are at the same height as each other, there's no delta y, so this term is 0. And even if you've got some strangely shaped pipe with different levels of fluid in it, maybe you've got like some fluid level here versus here, and for some reason they're at different levels. If you're comparing this location and this location, these 2 locations are at the same height as each other. It doesn't really matter that they're under different depths of fluid. The height is what matters when we're looking at the rho g delta y term. Of course, if you're comparing this point to the surface, that would matter. But if you're just comparing points 1 and 2, they're at the same height, regardless of depth under surfaces. Any questions on that height term?
So will they specify then if they mean like the difference in height? Like for example, in the bottom one that you drew, will I just feel like I mean I don't think there'll be a circumstance like this, but would they specify if they meant like the difference between the water level and the point and then the other water level and the point?
It's really a matter of what you're comparing. If you're comparing points 1 and 2, those 2 points are at the same height, so delta y is 0.
Yeah.
There might be some other differences, but there's no delta y.
Okay.
But let's say we put a point at the surface and we call it 3. So from point 3 to point 1, there is definitely a height difference.
Yeah.
And from, let's say, point 4 to point 2, there's definitely a height difference.
Yeah.
So from 3 to 1, there's a delta y. From 4 to 2, there's a delta y, and it's a different delta y.
I see.
From 1 to 2, there's no delta y at all.
Okay. Okay. Thanks.
We could probably conclude, for instance, from 3 to 1, we'd be gaining a certain amount of pressure. From 4 to 2, we'd be gaining less pressure because there's less height difference. So I would expect that 1 and 2 would be at different pressures, even though they're at the same height, which tells us it's not hydrostatic. There's got to be something else changing to make up for that.
I see. Okay. Okay. Thank you.
Any other questions on that so far? And speaking of pressure, are there any circumstances where we can be absolutely certain that delta P is 0? If we're just comparing 2 points, are there any times when we know they have no difference in pressure? In this system, for instance, are there any 2 points that you know have to be at the same pressure? When both sides, yeah, these 2 points right here, point 3 and point 4, those are both exposed to the atmosphere, so they have to be at 101 kilopascals of pressure. And that means they have to be at the same pressure. So if there's some reason where you know that they have to be at the same pressure, you can ignore that delta P. And that's usually if they're both exposed to the same atmosphere, or if they're both exposed to the same pressurized gas tank or something. Or maybe you've got pistons pushing on both points with the same amount of pressure. So this one's kind of flexible. Usually you do want to include delta pressure to possibly balance out other things. Like if there's some other changes in these that don't cancel each other out, delta pressure is usually what changes to balance out everything else. But if there are situations where you know 2 points have to be at the same pressure, such as, for example, if they're both exposed to the atmosphere, then you can ignore this. So you can ignore the delta pressure term if you know for certain, for whatever reason, that the 2 points have to be at the same pressure, such as, for example, if they're both at atmospheric pressure, if they're both exposed to the atmosphere. But don't fall into the trap of thinking same height means you can ignore delta pressure. Same height means you ignore the delta y term, but there could still be a delta pressure if it's not hydrostatic. Any questions on this side of the equation so far? And then on the other side, this one's a lot more straightforward, I think. You would ignore the pump term under what circumstances?
I mean, if you don't have a pump.
Ignore the pump term if there's no pump. One thing you do need to be careful about, though, if you have a system, I mean, if there's no pump at all, then of course you would ignore that term. If there is a pump, it's important to consider where it is. Like, let's say you have a pump in the system here. And let's say we label the point right before the pump 1, the point right after the pump 2, and then further down the line we've got location 3. If you're comparing 1 to 2, would you include the pump?
Are we comparing like in between there, or are we just literally comparing 1 and 2?
Yeah, that's the important question. If you're comparing 1 to 2, all of these deltas on the left side, delta only cares about initial and final. So anything involving a delta something, you just look at the value at 0.1 and the value at 0.2, and you don't care what happens in between. But the right side of the equation, the pump and the I times R, those do care about what happens in between. If you look at the path from 1 to 2, that path passes through the pump. So if you're writing out a Bernoulli equation comparing points 1 and 2, there's a pump on the path between those, so you would include the pump in your equation. But if you're going from 2 to 3, does that path go through a pump?
No.
So that means from 2 to 3, you would not include the pump. So what's really important is not so much, is there a pump in the whole system? What's important is there a pump on that path? So take a close look at the points you're comparing and actually draw out on whatever diagram you got, draw out a path from one point to the other. If that path goes through a pump, then you include the pump in your equation. If the path does not go through a pump, then you don't include a pump in your equation. But even if there's a pump in the system, you gotta ask yourself, does the path you're considering actually pass through it? Because the whole point of a pump is the pump creates a difference in pressure, or a difference in total energy density, really, the whole thing. The pump creates an energy density difference. High energy density on one side, low energy density on the other, by pushing on the fluid. Any questions on that so far? And then for the IR term, you can certainly ignore this if the fluid's not moving, if I is 0. But you can also ignore this if R is 0 or close to 0. And if resistance is, let's say, negligible. Physically, I don't think it's possible to build a pipe with 0 resistance, but you can design pipes with very, very small resistance. And do you know what aspects of the pipe play into how much resistance it has? Like if you wanted to design a pipe with a very, very small resistance, how would you design that pipe?
You want a pipe that has like low friction on the walls of the pipe, like you wouldn't want something that's like rusted. You would want something.
So if you can design the walls of the pipe to be very smooth, then that's going to lead to low resistance. Very smooth walls. And also the material of the fluid makes a difference there. The viscosity, really, that, like how thick, I guess you could say, the fluid is. So low viscosity fluid. And also the geometry of the pipe matters as well. Like for instance, the thickness. If you have a very wide pipe versus a very narrow pipe, which one do you think would be easier to flow through?
A wide one?
Yeah, very wide pipe means most of the fluid is flowing freely. Very little of it is in contact with the walls. Whereas with a very narrow pipe, most of the fluid is in contact with the walls, so you've got lots of resistance. So if the very wide pipe, if the pipe is very wide, you've got very low resistance. And also the length matters. The longer the pipe is, the more opportunities there are for the fluid to lose energy. So a very short pipe is going to have very low resistance. So if any of these things are true, or more vitally, if several of them are true, you can assume that the pipe probably has a very low resistance. If you've got a pipe with very smooth walls, if the fluid inside is very low viscosity, if the pipe is very wide, or if the pipe is very short, you can assume that it has very low resistance. Or if the problem just says assume resistance is negligible or ignore dissipation, then you can just treat R as 0 or close enough to 0. Physically, every pipe has a little bit of resistance at least, but if the resistance is small enough compared to everything else, then you can round that off to 0. Any questions on that so far? So let's take a look at some specific cases of this and see what happens. Specifically, let's focus on the pump for a moment and see exactly what the pump does. For simplicity, let's assume we've got just a straight horizontal pipe and there's a pump in it. And usually the pump has an arrow, direction. Let's say we represent that with an arrow saying the pump is pushing this way. If we want to figure out exactly what the pump does, let's compare a point right before the pump and a point right after the pump. If we wanted to write out a Bernoulli equation from 1 to 2, what terms can we ignore? What terms do we not need to include?
Delta y.
Yeah, there's definitely no delta y because points 1 and 2 are at the same height. Can we ignore anything else? Yeah, we can ignore speed here. Why can we ignore the kinetic energy density term? What's the only circumstances? Yeah, the area is the same. Points 1 and 2 have the same area. The only way the speed can be different, if we just got one path, one pipe, the only way the speeds can be different is if the areas are different. If these 2 points have the same cross-sectional area, they have to have the same speed. So don't fall into the trap of thinking that a pump causes a difference in speed between 1 and 2. 1 and 2 have to have the same current because of current in equals current out, the continuity idea. And if these are the same area, then they have to have the same speed as well. So a pump does not create a difference between a high speed zone and a low speed zone. These 2 zones have to be at the same speed. We definitely want to include a pump term because there is definitely a pump. We've got no delta V squared, no delta Y. Could there be a delta pressure?
Doesn't a pump change the pressure?
Yeah, so we should definitely include that delta pressure. And I wouldn't necessarily say a pump always has to cause a pressure change. The pump causes a change in the total energy density, the whole thing. And that could be changes in any one of those. But if we're looking at just before the pump and just after the pump, and we're assuming these aren't changing, pressure is the only thing left that can be changing. So there has to be a difference in pressure here because there's nothing else changing to balance that out. Should we include a minus IR term?
The pipe is pretty short.
Yeah, we are talking about 2 points that are very close together, or just barely to the left of the pump and just barely to the right of the pump. So if we assume that those are points very close together, we can probably assume resistance is approximately 0. That's not extremely realistic. Realistically, even the pump itself has some resistance. So there will be some resistance here. But if we assume this is a very smoothly designed pump and we're talking about a very short section of pipe and very wide and very low viscosity fluid, we can probably assume the resistance is close to 0. So the whole Bernoulli equation reduces to just delta pressure equals work done by the pump per unit of volume. So this is what a pump does. If you're looking at right before the pump and right after the pump creates a difference in pressure. It creates a distinction between a high pressure zone on one side and a low pressure zone on the other side. And usually the direction of this arrow, this is showing the direction the pump is pushing. The pump is kind of pulling on the fluid here, creating a low pressure zone. And the pump is pushing on the fluid here, creating a high pressure zone. So that's really what a pump does. The pump is physically creating a distinction between a low pressure zone on one side and a high pressure zone on the other side. And then whatever else that pipe connects to, maybe the high pressure and the low pressure influence other stuff elsewhere in the pipe. But if you focus on just the pump, all it's doing is creating a difference between a high pressure zone and a low pressure zone by pushing on the fluid. Any questions on that so far? Now let's try doing the same thing with resistance. If we look at a pipe with just resistance and nothing else changing. And sometimes we signify that by drawing the pipe kind of jagged. So maybe we've got a section of pipe made out of a rougher material. And we want to compare point 1 and point 2. With this path passing through resistance. So what would the Bernoulli equation look like for that path?
Would it be delta P is equal to work, the pump per energy density minus IR, because there's definitely resistance now.
Is there a pump along this path?
Oh, but there's no pump. Oh, so it's just negative IR.
Exactly. We can ignore the delta Y because these 2 points are at the same height. We can ignore the delta V squared because these 2 points are at the same area. Again, you can only change the speed if the area is changing. There's no pump. There is definitely a negative IR because, well, at least as long as there's current flowing. If there's no current flowing, this is going to be 0 anyway. But presumably, if you have current flowing through a pipe with resistance, you're going to get a difference in pressure. Points 1 and point 2 will be at different pressures because there's fluid flowing through a pipe with resistance. But this negative sign here, what do you think a negative sign signifies in a case like this?
The direction.
Yeah, the negative and positive here, at least with regards to current, is all about direction. So direction actually matters here. All the other stuff we've been looking at, there's not really any difference in terms of which direction current is flowing. But if the current is flowing, let's say current flows from 1 to 2. And let's say we're treating the Bernoulli equation as from 1 to 2. In that case, since current is flowing from 1 to 2, and we're treating 1 as if it's initial and 2 as if it's final, if you change to the middle of an area of resistance, like if you put point 2 in this region instead, there might be a difference in area, yeah. I mean, it might be the case that maybe the reason why there's so much resistance is because there's a pinch point. Usually the way you make a pipe have very large resistance is you make a narrower zone. Like for instance, if you got water flowing through a garden hose and you step on the hose, you're pinching it mostly flat. You're going to reduce the flow to a trickle because there's so much resistance in this narrow zone that it makes it difficult to flow. Now, if you're comparing point 1 here and point 2 here, regardless of the narrow zone in between, points 1 and 2 have the same cross-sectional area. So that wouldn't matter. But if you were comparing point 1 and point 3, then there would be a difference in area. And once again, this goes back to the idea that all these deltas on the left side, the deltas only care about initial and final value. They don't care what happens in between. But the right side of the equation, this is all about what happens in between. So you could even think of it as these are the things happening in between that cause the initial and final values to be different. But in this case, let's say we're talking about point 1 and point 2 outside of this narrow zone. So we don't really care about the values inside the narrow zone, just the total resistance of this section of pipe. One other thing about cutting it off at somewhere in between, if you're looking at a section of pipe that has resistance, but you only look at like half of that section of pipe, that half of the pipe will have half the resistance. The other half will have the other half of the resistance. Because resistance is proportional to length. The longer this section of pipe is, the more resistance it will have. Resistance is proportional to the length of the pipe. And it turns out that resistance is inversely proportional to cross-sectional area. So if you make the pipe twice as long, it'll have twice as much resistance. If you make it twice as much area, it's going to have half as much resistance. I think the dependence on area is actually slightly more complicated than that, but it approximates pretty well as inversely proportional. So the difference in pressure is caused by current and resistance. Resistance is just a property of the pipe. It's going to be a constant if you're looking at just one section of pipe that's not changing. So we'd say like this section of pipe has a certain value of resistance, and that doesn't change. The current could be changing depending on how much pressure difference there is, or vice versa. There's a couple of ways you could think of this. You could think of this as current flowing through a pipe with resistance causes a change in pressure from one point to the other. Or you could think of it the other way around. You could think of it as the difference in pressure causes current to flow. Like the pressure difference is the push that's making fluid flow through here. And it's not really that like one of those is more correct or less correct than the other. It's not really like one of them causes the other. These are just both happening. There's current flowing and there's a pressure difference. You could think of them as one of them causing the other or the other way around. They're both equally valid, I think. It really depends on the circumstances that you want to look at. You got to be careful about sign here, though. If you're looking at from 1 to 2, basically we'd be treating that as the positive direction. So you pick and and again, this isn't really time dependent. 1 and 2 are happening at the same time. But if you think of 1 as if it's initial and 2 as if it's final, from initial to final would be considered the positive direction. Is current flowing in that direction? According to this diagram, is the current flowing in the positive direction?
Yeah.
Yeah. Current's flowing to the right. We're calling to the right the positive direction. So current is a positive value. Resistance is always treated as a positive value by definition. But then we've got this negative sign. So delta pressure is going to be what? Yeah, we'll end up with a negative value for delta pressure. Because we've got a positive times a positive, that's positive. We apply an opposite sign, we get a negative value as the result. So from 1 to 2, we've got a negative change in pressure. In other words, pressure should be decreasing. We've got a high pressure zone to start with. And then point 2 is going to be a low pressure zone. So once again, we're talking about a distinction between two pressure zones, a high pressure zone and a low pressure zone. You could sort of interpret that as the pump creates a difference between a high pressure zone and a low pressure zone. And a pipe with resistance gets current flowing because of the difference between a high pressure zone and a low pressure zone. Or you could say the current flow creates a difference in pressure. That also works. If we try organizing this in the opposite direction, if we say we write out a Bernoulli equation from 2 to 1, like let's say we call from right to left the positive direction. Mathematically, there's no reason why we can't. We'd still write out delta pressure equals negative IR. R, as always, is a positive number. But if we're calling to the left the positive direction and the current's actually flowing to the right, what does that tell us about the value of I?
It's negative.
Yeah, current is going to be treated as a negative value. A negative value for current just means current's flowing in the opposite direction from the direction we're calling positive. We've still got a negative sign here, though. So that means delta pressure is going to be what sort of value?
Positive.
Yeah, delta pressure is positive. Meaning from 2 to 1, because here we're treating 2 as initial and 1 as final. From 2 to 1, we should expect an increase in pressure, going from low pressure to high pressure. But note that that's exactly the same distinction we got last time. Regardless of whether we're talking about from 1 to 2 or 2 to 1, if current's flowing this way, we end up with high pressure at point 1 and low pressure at point 2. Treating the coordinate system opposite in the opposite direction means we get opposite signs for I, but we still get this location is high pressure, this location is low pressure, regardless of what we call initial and what we call final. And yes, resistance is always positive by definition. A negative resistance would basically mean that the pipe, that the fluid gains more and more energy as it flows, which doesn't really make any sense. And note that the current is flowing from the high pressure zone towards the low pressure zone. That's another way to interpret this negative. This equation can be thought of as delta pressure is proportional to current. More pressure difference means more current. And the negative sign means that the current is flowing in the direction of decreasing pressure. Current's flowing from high pressure zone towards low pressure zone. In a problem when they specify, usually not. If you already know which direction current is flowing, it's usually easiest to just treat the direction current is flowing as positive. If you don't already know, just make your best guess or just choose a direction to call positive. And if you guess the direction that current is really flowing, you'll end up with a positive value for current. If you guess the opposite direction, that's fine. You just end up with a negative value for current. Why current is negative in the second example, it's really to do with what we're treating as initial and what we're treating as final. If we think of point 2 as initial and point 1 as final, so we're treating to the left as the positive direction, anything flowing to the left will be treated as positive, but the current's flowing to the right, so we have to treat that as a negative value. Doesn't matter whether we get a positive or negative. Yeah, the magnitude, the absolute value of I tells you how fast current is actually flowing in terms of liters per second or cubic meters per second or whatever. The sign just tells you direction. And it's really just a convention or almost like a coordinate system for direction. You just choose a direction to call positive. If the current is flowing in that direction, then I will be a positive value. If the current's flowing in the opposite direction, then I will be a negative value. So positive or negative is just describing the direction current is flowing. Any other questions on that so far? All right, one other quick thing, because somebody was asking about multiple fluid systems earlier. In any situation where you've got multiple fluids, like a common example is if you've got fluid flowing through a pipe. So you've got some current here. And you've also got a vertical pipe called a standpipe on top of it. And what's going to happen here is as this fluid flows, you get water rising up in the standpipe up to a certain level, and then it stops. So the water in the standpipe is staying still, but the water in the flow pipe is moving. And in that case, we have to treat these as two different fluid systems. The moving water and the stationary water have to be treated as different systems. Even though they're the same type of fluid, they're different properties. Moving versus stationary mean they're treated as different systems. What you can do, though, is you can, as usual, you can put a new point. You can mark a location at the interface where they're connected together. So let's say we call this point 1. And what would be the usefulness of causing another point up here? What do we know about that point up on the surface?
The pressure of it is equal to atmospheric pressure.
Yeah, this has to be atmospheric pressure. So let's call this point A for atmosphere. If we write out a Bernoulli equation from A to 1, what would the Bernoulli equation look like there? What terms do we need to include?
You would include delta y because there's a difference in height between A and 1.
Definitely a difference in height. And let's call that difference in height h. Let's say h is the height that the water level rises to. Any other differences between point 1 and point A?
I mean, the pressure is different.
Yeah, we should include a difference in pressure. Presumably this is going to be at a different pressure than 1 atmosphere. And just the fact that we don't know that they're at the same, that there's no information suggesting they have to be at the same pressure means we should include delta pressure just in case it's needed. Is there any difference in speed between point A and point 1?
No, it's stationary.
Yeah, because even though point 1's on the border between stationary water and moving water, for purposes of this path, we treat it as being part of the stationary system. We could then later, like let's say we were comparing it to a point 2 further down the line, along this path, we would treat point 1 as part of the moving water system. But along this path, we treat point 1 as part of the stationary water system. Since it's on the surface, on the border between them, we can treat it as part of either one, whichever one's convenient. So we're going to treat point 1 as being part of the stationary system. There's no change in speed. There's also no pump in this standpipe. The standpipe could certainly have resistance, but there's no current in that section. So for purposes of the standpipe itself, we're going to be using the hydrostatic equation. Delta pressure equals negative rho g delta y. So we could write this as pressure 1 minus 1 atmosphere equals negative rho times g. And then from A to 1, would you treat delta y as a positive or negative value? From A to 1, are you moving up or down?
Down.
So we're going to treat that as would that be a positive or negative change in height?
Negative.
Yeah, we'll write that as negative h. You can even think of that as final minus initial. If you treat this as height 0 and this is height h, 0 minus h would be negative h. So we end up with P1 minus 1 atmosphere. The negatives cancel out. You just get rho gh. And you could add 1 atmosphere to both sides and say pressure 1 is 101 kilopascals plus rho gh. Or we could look at this in terms of gauge pressure. In terms of gauge pressure, we just ignore the 1 atmosphere and say the gauge pressure of 0.1 is rho gh. This means that a standpipe like this is a very convenient way of measuring the pressure in a fluid system. You put a standpipe here, measure the height it rises to, multiply by 10,000 for water, or in general, density times gravity, and that tells you the pressure at the bottom of the standpipe in that mystery fluid system. In fact, a very convenient way to use this, instead of, like usually you'll have markings on a standpipe like this. Instead of marking it in centimeters, you could mark it in pascals. You could mark this as like 10 pascals, 20 pascals, 30 pascals, 40 pascals, and so on. If you got it marked off like this, if it's already been calibrated, you just look at how high the water rises, read off the number of pascals. That tells you the gauge pressure and the fluid at the bottom. So a very useful way of visually measuring the pressure inside some fluid system. Just look at how high the water rises in that standpipe. Any questions on that? And so you can use that as a general rule. The gauge pressure at the bottom of a standpipe is density times gravity times the height that it rises to in that standpipe. So keep that in mind. We're going to be using standpipes a lot in examples of fluid systems like fluid flowing here. And the standpipe is essentially a pressure gauge.
All right. A quick question.
Okay, go ahead.
So when you're doing the gauge pressure, so if we're trying to find the pressure for 1, the height we would use is the height of A.
Yeah.
And that's like, okay, you'd use that height between A and 1.
Yeah. And so basically you just, like if you had a ruler taped to the side of the standpipe with 0 here, you could just measure how high in centimeters the water rises, convert that to meters, multiply by density and gravity, and you get the gauge pressure at 0.1. If you want absolute pressure, you could just add 1 atmosphere to that. Any other questions on that? All right, then I will see you next time.
Thank you.
You're welcome.